Hello class, welcome back to our course Engineering Economy. Today we're going to discuss arithmetic gradient. So if you recall our discussion previously on interest formulas, we started with computing for a future value of a present amount of money given an interest rate I over n interest periods, and then we proceeded with computing the um, present worth of a future amount of money given an interest rate I and over n interest periods. After that, we discussed the equivalent annual payments over n periods of time with an interest rate I, given either a future amount of money or a present amount of money. So we call the last discussion the uniform payment series, or the annuities that we have derived the formulas before. Now, so of course, in that discussion, we recall that the amount A is a uniform amount over the n interest periods, and having a uniform or a fixed interest I. So today we discuss the arithmetic gradient, which is the series of cash flow that either increases or decreases by a constant amount each period, and the amount is called the gradient. So in other words, compared to our previous discussion, A, which is uniform and equal all throughout the interest period, here we have an amount that increases at a constant rate. So by a constant amount each period, and we call that again a gradient. So we look at this cash flow diagram, which shows you a series of amounts from 0 to n interest period, and we start off at the first interest period 1 at $2,500, and it goes up, and this becomes 2,700 at the end of the second interest period, and then goes up again at 2,900 at the third interest period, and so on and so forth. And we have at n minus 1 interest period, you have 2,500 plus n minus 2 $200, which is the gradient that we talk about. So in other words, if you look at the amounts, you can see that it progressively increases by $200 every end of the period. So at the nth period, at the end of the nth period, you will have a $2,500 plus n minus 1. Let me just add here the amount $200, right? So the base amount in this increasing money or deposits is 2,500, right? So that's your base amount. So if you remove that base amount from the original cash flow diagram, you will end up with this cash flow diagram, where we denote the $200 as G, which is our gradient. So notice that while in other discussions we always start with the annuity or the uniform cash payment or deposit at the end of the first period, here notice that G starts at the end of the second period. So we say that at the second n is equals to 2, we have g, and at n equals to 3 we have 2g, and at n equals to 4 is 3g, so on and so on and so forth. And we have at n minus 1, we have g times quantity n minus 2, and then of course at n, at the end of the nth period, we have n minus 1 times g. So again, g is the constant arithmetic change in cash or in cash flows from one time period to the next. So it could be positive or negative. So you can have it either as a withdrawal, as a deposit, as an earning, as a cost. So it's either a negative or positive number. And we can denote the cash flow at that particular period. Let's say cash flow at n, so is equal to the base amount plus n minus 1 times g as the cash flow for that year n. So basically, we bring back the base amount here, and then we add this cash flow there, and you'll still end up with this cash flow formula, which is equal to the base amount plus n minus 1 times g. So let's further clarify that with an example. So here we have an estimated revenue for the first year of $80,000 and increases uniformly to $200,000 by the end of year 9. So we are asked to solve for G and to draw the cash flow diagram. So we go back to our formula. The cash flow at year N, or the end of year N, is equals to base amount plus the quantity N minus 1 times G. So by the end of 9 years, right, on the 9th year, end of the 9th year, our cash flow is CF sub 9 is equal to base amount plus 9 minus 1 times G, which is, plugging in all the given numbers, we end up with 200,000 equals to 800,000 plus 8G. Solving for G, you will have $15,000 per year. So drawing the cash flow diagram, you will have 0 to 9, that's your interest period, and the first or the base amount is 80,000, and it increases uniformly by $15,000 every end of the year, succeeding years, up to the 9th year where it goes up to $200,000. So that is the concept of having a deposit or revenue that increases at a certain amount every year. So this clearly shows you the concept of the arithmetic gradient. Now, but of course, we are really interested in computing the equivalent cash flow or values of money, and always we want to determine what is that value at the present. So essentially, the present worth, the total present worth, in other words, for this cash flow, for this arithmetic gradient cash flow, is going to be the present worth of the fixed or the base amount, right? And then plus or minus, because our gradient could be positive or negative, the present worth of the gradient cash flow. So there, where P sub t is the total present worth and PA is the present worth of the uniform series, and PG is the present worth of the gradient series. So it's just again, computing for the present worth of this here, of this cash flow, computing for this present worth of this cash flow diagram is just adding the present worth of the uniform series and the present worth of these gradient series. So that's just the total. If you add that those quantities, you will have the present or the total present worth of the cash flow. In the same manner that if you want to compute for the annualized or the equivalent annual worth, right, of these cash flows, so it's just equal to the annual worth of the base series, right, and the plus or minus annual worth of the gradient series here. So that's basically how you just combine the effects or the worth of each component. So by we can show that by showing the equivalent cash flow diagram here below. So recall our cash flow diagram for the gradient alone, right? So this gradient, which starts at end of year 2, n equals to 2 is g, and then increases progressively by an amount g. So we can actually solve for the equivalent present worth of this gradient at t equals 0 or n equals 0 using the the present worth formulas that we have earlier derived. So recall that here, let's go. So recall that the present worth for a given amount of let's say future payment, right, is equal to the present worth of compound factor, which is P over F at interest period I over n interest period. So we can use this to compute the aggregate or the cumulative effect of every gradient at each n period to PG, right? So that's simply applying this formula here to the individual gradient amount, and you will end up with this series of terms. And this will basically, after doing your arithmetic operation, that will give you a PG equal to the G times the quantity 1 over 1 plus A squared plus 2 over 1 plus A cubed plus 3 over 1 plus I to the fourth plus, and then with ending up with n minus 1 1 plus I, because this is here you end up at n minus 1 G. So this is the one here that corresponds to that factor. So by basically multiplying this equation A here by 1 plus I on both sides of the equation, you will end up with this equation B. So if you notice, if you multiply 1 plus I here, this becomes 1 plus I, right? Because it cancels the first power exponent, and so on and so forth. So it ultimately reduces your exponent at the denominator by 1. So this is the resulting equation. And we can further simplify this equation B here by subtracting A from B. So remember that in our basic algebra, if you subtract like say, for example, if you have f of x equals to g of x, and if you subtract another function here on both sides, let's say by say h of x, this is still equal to the same equation, right? You recall that. So subtracting the same amount or the same quantity on either side of the equation will result in the same thing. So that's what we're doing here by subtracting a from b and simplifying. So you get this one here, this formula. You can do this on your own. Try to practice and see if you come up with the same formula. So well, we can illustrate that essentially. So what will happen here is, let's do this. All right. What will happen here is that this term will combine with this term, right? Right here. And all of course you will carry all the denominator because you're just subtracting, right? So it results into this, and this, because the first one here doesn't have the same term on the equation a, so this is the one here that's carried down here, right? And then all the rest will have the numerator subtracted by the first by the formula a. So for example, here this will be 2 minus 1, right? This will be that. And here 3 minus 2, right? This will be that, and so on and so forth. So you will end up, but here this whole thing here will be this one here, because it doesn't have any like similar term, so you cannot really combine them with any other terms there. So simplifying this operation will give you this formula for the present worth of the gradient, which is equal to g over I, and this whole term here, right? And this whole factor here, which we can basically denote as this factor here is the arithmetic gradient present worth factor. So you will have a table for the common interest rates, but if the interest rates if your interest rate that you're using doesn't show in the table, then you have to use the formula, right? This formula here, the complete formula. And so that's the arithmetic gradient present worth factor. Now remember that the arithmetic gradient starts at year 2, as we mentioned earlier, and P is located at year 0. So again, we recall from our previous formulas that to compute the annual worth given a present worth amount or value, this is the formula that you will use, right? So this is the annual worth factor, or uniform series annual worth factor here. So applying that to the equivalent annual worth of the gradient, then you just use the same PG, which is the present worth of the gradient, right? And then you multiply again with the with this factor here. This is the uniform series annual worth factor. So substituting your formula here, right? You have this formula, substituting it here, right? So you end up with this one, right? So just substituting the factors, the formula for the factors, and simplifying them, try to do the simplification. Like for example here, this is the corresponding present worth gradient formula, and this is the corresponding annual worth uniform series annual worth factor. So you just distribute it here, right, and you will end up with this expression. So simplifying further, you will have this expression for the equivalent annual worth of the gradient, right, where we call this factor here, this factor as the arithmetic gradient uniform series factor, denoted by the quantity a over g with at interest rate I over n period. So that's the arithmetic gradient uniform series factor. So this is how it basically looks like now. From a arithmetic gradient cash flow diagram, you are able to convert your cash flow into an equivalent annual payment, which is denoted by AG, just to distinguish it from the uniform annual worth amount. And so basically that's the equivalence. So that's the economic equivalence of these two cash flow diagrams. Again, let's recall the formula for future worth given a uniform annual amount A. So that's F equals to A times the this is the compound worth factor, or the annual uniform series amount factor, annual uniform series amount factor, F over A at interest rate I over n periods. So therefore the future amount, the future equivalent amount of a annual equivalent amount with gradient G is just a similar equation, right? It's just a similar equation. The difference is just the sub notation here, G. Okay, so so again, we recall that we already derived the formula for the annual annual worth amount for a gradient cash flow. So we just substitute the formula here, and you'll get this expression. Again, you can practice this on your own and see if you come up with the same formula here. So again, where this whole factor here, right, will be called the arithmetic gradient future worth factor, right? So this is the notation that we use in finance or engineering economy. All right, so let's proceed with an example. So we have here neighboring parishes in Louisiana have agreed to pool road tax resources already designated for bridge refurbishment. At a recent meeting, the engineers estimated that a total of $500,000 will be deposited at the end of next year into an account for the repair of old and safety questionable bridges throughout the area. Further, they estimated that the deposits will increase by $100,000 per year for only 9 years thereafter, then cease. So we are asked to determine the equivalent present worth and the annual series amounts if public funds earn at a rate of 5% per year. So essentially the required here is the equivalent present worth, PT, and the equivalent annual series amount, AG. All right, so we draw the cash flow diagram to show the annual amount and the increase, which is here shown. It starts at $500,000 and ends up at 1.3 million after 9 years, right? So basically, you start at 0 and end at the 1 plus 9. So here it's very easy. It's already given that G is equal to 100,000. So that's already given. And interest rate is also given at 5% per year. Now, from our previous equation, the equivalent present worth is just equal to the individual present worth of the base amount and the present worth of the gradient. So directly substituting our formula, you can actually go back to your compound interest tables and get these factors here, or you can use the formula and plug in the numbers and you will more or less get the same values. So this will result in a $7,026,000 present equivalent worth of the base amount and the increases. And for the annual the equivalent annual worth, sorry, so we have to change this one here because I mistakenly showed it as 80, but it should be 80, right? So the equivalent annual worth is the same, the contribution of the base amount and the gradient. So it's a direct substitution of our values. Then we will end up with the $909,910 every year. So or if you want, you can use the formula. So now that you have here, you have given here the present amount or the present worth of this gradient, you can use the formula for the annual worth, right, which is given present amount. What is A, given that the interest rate is 5% over 10 interest periods. So you can look this up in your interest table and you will get this value here, and you more or less you'll get the same answer. So this wraps up our discussion on the arithmetic gradient. I'll give you your assignment separately, and next lesson we're going to discuss the geometric gradient for cash flow. I'll see you again next time. Thank you. Bye.